Swayam Prabha. Digital India. Educated India.
So in this lecture, we are going to talk about convolutional neural networks. So let's start. So first, let's define something known as a convolution operation. So how many of you have seen the convolution operation before? How many of you know what a convolution operation is? Okay. Not many. So let's take a very simple example. So suppose you're tracking the position of an aeroplane using some laser sensors at discrete time intervals, right? So after every 10 seconds or 30 seconds, you are measuring where the aeroplane is, right? So suppose the flight taking off from Goa to Chennai, and after every 10, 15, 30 seconds, you are measuring how far the flight is from Goa, right? But it's possible that there's some error in your sensor on your measuring equipment. So instead of relying on the current measure, you want to rely on all the previous measures, right? So instead of just relying on the measure taken at time step 2, you would want to take an average of several measurements that you have taken so far, right? So this is what you would want to do. So you look at this quantity. So xt, x subscript t, is the current measurement that you have taken at time step t, right? So you are taking measurements at time step 1, 2, 3, 4, and so on. And these time steps are, say, 30 seconds or 1 minute or 2 minutes apart. So at time step t, you have taken a certain measurement. But you know that your laser is noisy, so you don't want to rely on that measurement alone. You want to rely on all the previous measurements that you have taken so far, right? So from xt, which is your current measurement, you want a revised estimate, st, based on all the previous measurements. So what you're doing is, you're basically taking a weighted average of all the previous measurements that you have taken. Okay, now without knowing anything about convolutions or anything else, can you tell me, if you're at time step 100 and you're measuring this distance based on all the previous 99 readings that you have taken, what are the weights that you will assign to the reading 99, and what is the weight that you will assign to the reading 1? Just tell me in terms of high and low. 99 would be high because that's the more recent measurement. So that means you have, say, already moved some 200 kilometers away from Goa. And now the previous reading would have been, say, 190 kilometers or something. But at time step 1, the reading would have been 5 kilometers or so on. So if you take a weighted average with that, you're going to be pushed closer to 0 as compared to 200, right? So you would assign more weight to the most recent recent measurements and less weight to the far off measurements, right? So you're taking a weighted average of all the measurements that you have taken so far, starting from time step 0, okay? Starting from the all the way back to the first time step up to the current time step. So don't worry about this 0 to infinity. I'll just change it in a minute and it will become clear, right? And all of us agree that these weights should be in some kind of a decreasing order. The most recent reading should be given a higher weightage, and the far off reading should be given a lower weightage. Is that fine? So now let's understand what this equation is saying, right? So let's expand this term, okay? So let's make it 0 to 10 instead of 0 to infinity. So now can you help me? What's the first term going to be? xt minus? A goes from 0 to 10. So the first xt into w0. Then the next one is going to be xt minus 1 into w minus 1, and so on. All the way back up to x. T minus t would be 0, so x0 into w minus t. Does everyone get that? How this formula will expand? So there are so many terms in this formula. And this formula is compactly written as the following. How many measurements do you have? Suppose you are at time step 100. How many measurements do you have so far? 100. How many weights do you have? 100. So you can think of measurements as a vector of size 100. And you can think of the weights as a vector of size 100. So it's a element-wise multiplication between these two vectors. The 100th entry here gets multiplied by the 100th weight. The 99th entry here gets multiplied by the 99th weight. Is that okay? Right? So this element-wise multiplication of these two vectors, we're going to write it as the convolution operation. Okay? So you have the input, which is x. You have the convolution operation. And you have the weights, which are also known as filters, because in some sense, it tells you which are the quantities to filter out. Right? Because you're going to assign weights lower weights to the least important entries and higher weights to the more important entries. Is that fine? A very rough explanation of that. So let's look at this in more detail. So now instead of 0 to infinity, I've taken it to 0 to 6. So now what I'm saying is, my new computation of ST is not going to depend on all the previous infinite measurements that I've taken, but it's only going to depend on the previous 6 measurements that I have taken. Does that make sense? How I've changed from infinity to 6? Is that fine with everyone? Huh? Okay. So then how many weights do I need? 6 plus 1. 0 to 6, right? Okay, so 7 weights. I have to assign weight to the current reading also, right? And so my weight vector is of what dimension? 7. There are 7 weights, so there are 7. It says, okay. And I have an X, which is all the measurements that I have taken so far, and I'm going to continue taking the measurement. So I'm at that particular reading, which was 1.90. Okay? Do you see that reading 1.90 in the X vector? Now that's XT, and I want a revised estimate for that. I want to compute ST using XT. And how am I going to compute that? X6 into W0, X5 into W minus 1, X4 into W minus 2, and so on. Does everyone see that? Just expand out that formula. Anyone has a problem with that? Please raise your hands if you did not understand this. If you don't understand this, you'll not understand anything after this. Just focus on the math part of it, not the why, the intuitions, and so on, right? Do you get the math part of it? Okay. So now tell me, if I want a revised estimate for 2.10, what will I do now? I'll just move this weight vector by 1 and do the same operation. W0 into 2.10, W minus 1 into 1.90, W minus 2 into 1.80, and so on. Does that make sense? Is everyone okay with this? Are you fine with this? You don't seem too okay with this, no? Ask me specific questions, I can answer. So what I'm doing is I'm taking a weighted average of all the formula you understood, right? So this is just a computation of that formula, right? So that's nothing. So I've just expanded it out. X6 into W0, X5 into W minus 1, and so on. So actually I think there's an error here or not. Yeah, it should have been X6, X5, X4, X3, X2, X1, X0, right? I think I started decreasing and again started increasing that. So the last 3 terms should be X2, that was your confusion? Okay. X2, X1, and X0. Okay, in this equation. Fine. Okay, so now this is what a convolution operation looks in one dimension, right? So you have these one-dimensional readings, and I had applied a convolution operation to get a weighted average of all my readings. Now, can you apply the convolution operation to a two-dimensional input? Do you know of any natural two-dimensional inputs that you deal with almost on a daily basis? Everyone? Images. You can think of images as a two-dimensional input. It's a matrix. It has 30 cross 30 pixels, right? So you can think of it as a two-dimensional input. Now, in the case of this measurement, what the convolution operation was doing is, it was giving you a weighted average of your inputs. Now, in the case of an image, what would an equivalent operation be? So what are the measurements or what are the values in my image? They are the individual pixels. So for each pixel, I have a value. Now again, I have the same setup that maybe my camera was faulty or maybe my compression algorithm was not good and the image is slightly noisy. And I want to compute a new image by taking a weighted average of all the pixels around it. So how will I do that? Can you apply the convolution operation to a two-dimensional input? So remember in the one-dimensional input, I had a reading matrix which was very large, right? Now for any particular reading here, I was revising it using a small window of weighted average, right? A large input, one particular reading obtained by a small window of weighted average. Now I have a two-dimensional input. I want the revised estimate for one pixel here. How will I get that? I'll take a weighted average of dash around it. Pixels around it. Does that make sense? Is that everyone fine with that? Okay. Now the only thing which remains is how do you convert this into a equation, right? So this is how you'll do it. So suppose you wanted a revised estimate for A. A was your original pixel value. So think of this input as a 4x3 image, right? And you want to compute a revised estimate of it by using a 2x2 neighborhood. So the kernel here or the filter here is 2x2. Just as in the earlier case, you had a window of 6, here your window is 2x2. So you're going to paste this 2x2 kernel on this pixel, right? And take a weighted average of all the neighbors around it. So that's exactly what that would be. A into W plus B into X plus E into Y plus F into Z. Everyone understands this operation? Everyone sees the analogy of this with the one-dimensional case? A weighted average of the neighbors. The neighborhood was 6 pixels there. Here it's a 2x2 neighborhood. Everyone gets this? How many of you get this? Please raise your hands. Okay, fine. What would be the revised value for B? Relate the two? Okay. So in that case, you had these many measurements, all the measurements. For a given value measurement, you were trying to find the revised measurement. So you relied on the neighborhood around it, right? And you did that. And you did a weighted sum of the neighborhood. Now you have a two-dimensional input, right? You're focusing on one particular pixel there. Just the A. And remember, there also for every value you had computed a revised estimate, right? So here I'll start with 1 and compute it for everyone in the image. So for A, I want to find a revised estimate. So just as in this case, the neighborhood was one-dimensional, now I'll look at a 2x2 or a n cross n neighborhood around it, right? And I'll take a weighted average of all the pixels there. Is that fine? Okay. Now I have given you the formula for the revised estimate for A. Give me the formula for the revised estimate of B. BW plus CX plus FY plus GZ. Everyone gets that? Okay. And I can continue in this way. Do you notice something about the dimensions of the input and the dimensions of the output? Smaller. Why is it so? Okay, so we'll come back to that. So just for now, observe that the output is smaller. Everyone observes that, right? I mean, that's straightforward. Okay. So for the rest of the discussion, so now what I've done is, in this case, one way of saying it is that when I was interested in A, I was looking at all the future neighbors of A, right? I was looking at the pixels to the, what is that on your side? It's right and at the bottom, right? I was looking at the pixels on the right and the bottom. But a more proper way of doing this would be what? To look at pixels around it, right? Not just right at the bottom. So what we'll do is we'll use the following formula. So you see that I'm going from minus m by 2 to plus m by 2, right? So that means I'm looking at the neighborhood. So don't focus on the formula, just focus on the image that is there. So for a given pixel of interest, I'll place the filter on that pixel and I'll look at all the neighbors around it. That means left, right, top and bottom. Earlier I was just looking at right and bottom. Now I'm looking at left, right, top and bottom. That makes more sense, right? Have all the neighbors around it instead of just having neighbors in one direction. Is that okay? Fine. So that's the convolution formula that we'll use now. So let us look at some convolution operations applied to an image. So I give you this image and I ask you to apply the following convolution to that. So let's first understand the meaning of this. What I'm going to do is for every pixel in the image, I'm going to place that filter on that image, take a weighted average based on these weights, and compute a new value for that pixel. Okay? And I'm going to do this for every pixel in the image and give you a new image. So what's the new image going to look like? Same. Distorted. Softer. Okay. Smaller. Okay. Just ignore smaller for now. How many of you have used Adobe Photoshop before? What are some of the operations that you have used there? Sharpening, blurring. Okay. Now, can you tell me what this would do? So I'll give you some hints, right? So try to realize what would happen when you place that pixel, this kernel at a pixel which is on that white edge of the dome, right? You have this dome of the Taj Mahal. If you place it at the pixel where some of the neighbors are blue and some of the neighbors are white, what will happen? What will happen? It will become blurred, right? So that is exactly what will happen. The image will become blurred. So in Photoshop, when you apply this operation of blurring, right, it's basically applying this convolution I don't know how Adobe works, but one way of doing that is this, right? You could apply this filter throughout the image and you'll get a blurred image. Does that make sense? Okay, so let's look at another filter. What will happen if you apply this filter? Okay, if we did blurring, the next one has to be sharpening. Why? What is this trying to do? It's increasing the weight of the center and decreasing the weight of the surrounding. So if whatever is in the center which is similar to the neighbors, that will go down and the center will emerge, right? Does that make sense? So then the image will become sharper, okay? It may not be obvious here, but if you look at the slides or in a better resolution, you will see that the image has actually sharpened, okay? What about this? So I'll tell you how to go about this, right? Apply it on a portion of the sky. Apply it on a portion of the dome. Apply it on something on the lawns, and then apply it at the boundary of these things and see what will happen. If you apply it at the sky, this pixel is blue. All the neighboring pixels are also blue. What will happen? 0. Give me the answer. If you apply it to the sky, you're taking -8 times the current pixel and adding all the neighboring pixels. How many neighboring pixels are there? 8. If all of them are same, what will happen? 8 minus 8, right? So it will become 0. So at regions where everything is uniform, what will you get? Black. At the boundaries, what will happen? You'll get some value, right? Something different will happen there. So then what will happen in effect? It will give you all the edges, right? It will give you the skeleton of the image. Does that make sense? Okay. Have you seen this before? Right? So this is how the convolution operation works. So now if you understand these outputs, then I'm confident that you understand what the convolution operation is. You have to take this filter, apply it at every pixel, and come up with a new pixel value. Does that make sense? Okay. Fine. So now we'll see a working example of a 2D convolution. So this is my image. Assume that each of these black boxes is 1 pixel, right? Of course, it's not 1 pixel, but for the sake of simplicity, assume that it's 1 pixel. Now I'm going to take a 3x3 kernel and place it on each of these pixels with that pixel at the center. And I'll compute this weighted sum and I'll get 1 value. So every time I move this filter, I'll get 1 value, right? And I keep moving it throughout the image to reconstruct the entire image as a weighted sum of its neighborhood, right? And when I did this in the previous 3 examples, I got those effects of blurring, sharpening, and edge detection. Does that make sense? Okay? Fine. So this resulting output is called a feature map. So why is it called a feature map? We'll get to that later on. So this is called a feature map. So you had the original image. Now you have some transformation of that image. Okay? Some output of that image. Okay. So in the 1D case, we slide a one-dimensional filter over a one-dimensional input. This is what we did in the 1D case. Is that fine? This is how we were sliding it. In the 2D case, we did the following. We had a 2-dimensional filter which we were sliding over a 2-dimensional input. Is that okay? What would you do in a 3D case? First of all, do you know of any 3D inputs? The hint is, the answer is the same as that you gave me for the 2D input. An image is actually a 3D input, right? Because it has these pixels and then you have these 3 channels, red, green, and blue, right? So you can think of an image as a 3-dimensional input, okay? So we are still dealing with images only if you go to 3D. So what would a 3D convolution operation look like? So in 1D case, we are taking a aggregation of the neighbors in that 1 dimension. In the 2D case, we are taking an aggregation of the neighbors in 2 dimensions. What will you do in the 3D case? Aggregation of the neighbors in 3 dimensions. So what would that filter look like? A cuboid. Does everyone get that? Right? Okay. Now, so this is your RGB 3-dimensional input, and your filter would look something like this, right? As you said, it will be a cuboid. And what I'm going to do is, I'll start placing this cuboid at every pixel, right? And for every pixel, I'll aggregate the 3D neighborhood around that, okay? And what will I get? I'm taking an aggregation of a 3D neighborhood for 1 pixel. How many values will I get in the output? 1. every convolution operation will give you one value, right? It's taking an aggregate of all the neighborhood but giving you one value. It's summation Wixi, right? Roughly. Is that fine? Everyone understands that? Everyone? Okay. So I slide this throughout and I get what is the output size now. I started with the 3D input. What is the output? Y. 1D, the output was 1D. 2D, the output was 2D. So in the 3D case, why is the output 2D? Yes. So roughly, the choice of words is different, but I think your answer is correct. So in the 1D case, we are sliding this way. In the 2D case, we are sliding horizontally and then vertically. In the 3D case, what should I have done? Horizontally, vertically, and then across the depth. Did I do across the depth? No, because I assumed that the depth of the filter is the same as the depth of the input. That's why I could only slide it once. I could not slide it anymore. Right? I had 3 channels, and my depth of the filter was also 3, so I cannot slide it anymore. Does everyone get that? Right? So that's what we are actually doing is, we are applying a 2D convolution operation to a 3D input. Okay, because we are only moving in the vertical and in the horizontal and the vertical direction. We are not moving along the z-axis. Does that everyone get that? And for the rest of this lecture and for most of convolutional neural networks, you will be dealing with 2D operations on 3D inputs. That means your depth of the filter will always be equal to the depth of the input. Everyone gets that? Okay? So that's why when I apply a 2D convolution on a 3D input, I'll get one 2D output. Okay? Now suppose I apply one more filter. What will I get? So this was one 3x3 filter which had certain weights. Okay? So suppose this was the blurring filter. I could also apply the sharpening filter. I could also apply the edge detector filter. Now what will happen with each of these filters? For one filter, I got one 2-dimensional output. For the other filter, another 2-dimensional output. For the third filter, and in this way, what will I get? I'll get multiple 2-dimensional outputs. So that means I'll get a 3-dimensional output, right? So I had one filter, one 2-dimensional output. Second filter, another 2-dimensional output. Third filter, another 2-dimensional output. So I have 3 2-dimensional outputs. That's the same as saying that I have one 3-dimensional output with depth equal to 3. Is that okay? Everyone gets that? Anyone has a problem with that? Okay. So now let's look at the relation between the input size, output size, and the filter size. Okay. So we have not said anything about the sizes of the inputs, the outputs, and the filters. So let's see. So this is my generic input, which is of width W1, height H1, and depth D1. Now, there's something known as the stride of a filter. So I'll come back to the stride later on. And there is something known as, there's no F here. The number of filters K. So I said I could apply the depth, the blurring filter, the sharpness filter, the edge detector filter. So I have K such filters. And for each filter, I'll get one 2-dimensional output, right? So I had 3 filters here, so I'm getting 3 2-dimensional outputs. And I'm saying that the spatial extent of the filter is F. What does that mean? The size of the neighborhood is F cross F. It's obvious from the image, right? So when I say that the spatial extent of a filter is F, what I mean is that the size of the neighborhood that I'm aggregating over is F cross F, right? But I have a 3D convolution. So then how can I only mention F cross F? I also need to mention the depth, right? The assumption is the depth is the same as the input. Is that okay? That's why I only need to mention the width and the height. Is everyone fine with that? So input of size W1, H1, D1, filter of size F cross F, and K such filters. And now what do I want to tell you? This is going to produce some output. What do I want to tell you? The dash of the output. The dimensions of the output. What is W2, H2, and D2? Is that fine? All of us intuitively observed that there was some reduction in the size, but I need to tell you what the formula is now. Is that okay? Fine. So the output is going to be of size W2, H2, D2. And I need to tell you what is W2, what is H2, and what is D2. Okay? So I have a 3D input. I'm applying multiple 3-dimensional convolutions to them. But each of these convolutions, I'm going to do a 2D convolution operation. That means I'm going to only move around the vertical axis and the horizontal axis and the vertical axis. I'm not going to move across the depth. Okay? And now I need to tell you after this operation, what's the output size going to be? That's the same as saying what is the W2, H2 and D2 going to be. Okay, fine. So let us compute W2 and H2 first. So let's consider the simple case where you have a two-dimensional input, and now I apply a 3x3 filter to it. What's the size of the output going to be? So my input was 7x7, and I applied a 3x3 filter to it. What's the size of the output going to be? At least from the figure. 5x5. Why? Yes. Because I cannot place the filter here. I cannot place it anywhere in the last column. I cannot place it anywhere in the last row also. I cannot place it anywhere in the first column, anywhere in the first row. So I have one column subtracted from the left, one column subtracted from the right. So how much will the width decrease by? 2. And how much will the height decrease by? 2. So what's the formula for W2 in terms of W1? W2 is equal to W1 minus 2. Always? It depends on the filter size. How does it depend on the filter size? So let's remember this. When the filter size was 3, the width decreased by 2. All of us agree with that? Okay. Now let's see, suppose I had a 5x5 filter. Now, which are the regions in which I cannot place the filter? First and second row. Second last and last row. Last two columns, first two columns. So the width will decrease by how much? First two, last two. 4. And the height will decrease by 4. So when the filter size is 5, the width decreases by 4. When the filter size was 3, the width decreases by 2. Now can you give me a formula? W2 is equal to W1 minus W1 minus in bracket K minus 1, right? When it's 3, it's 2. When it's 5, it's 4. Does that make sense? Okay. So the formula that you have is W1 minus bracket F minus 1. So when you open the bracket, it would be W1 minus F plus 1. And the same formula for H2 also. Right? Same thing for H also. Everyone gets this? Please raise your hands if you get this. Up and high. Width and height. So W2 is the width of the output and W1 is the width of the input. No, right? Because you can't place the filter. If you place the filter at that 1, 1 pixel, half the filter would be outside, right? Then how will you take the weighted average? You don't know what pixels are there. Do you get that? See this. If you place the filter there, the same thing will hold at the top corner also, right? And anywhere in the top row, half of the filter or some portion of the filter would be outside. And you don't know. So it's like you have the weight, but you don't know what's the input to multiply it with. Does that make sense? Okay. Now, but what if we want the output to be the same size as the input? So when we were doing this Taj Mahal variations, we wanted the same size of the output. So what do we do if you want the output to be same size as the input? What is padding? Extra pixels on the... Okay. So now, suppose I have a filter size. So everyone got what padding is? So what I'm going to do is, I'm going to take, if I have a 3x3 filter, I'm going to add a padding of size 1. Okay? Now I can start putting the filter at the 1, 1 pixel. Right? Because I know that the neighborhood around it is all zeros, and now I can do a weighted average of that. Does that make sense? So if I have a 3x3 filter, I know that the width decreases by 2. So if I want the width to be the same, how much padding should I add? I should add a padding of 1. So when I say a padding of 1, it means 1 extra row, 1 extra column on the left, right, top, bottom. Right? So padding of 1 effectively means 2 extra rows and 2 extra columns. Does that make sense? Okay? Now if I have a filter of size 5 cross 5, how much padding should I add? 2. 2 on the left, 2 on the right, 2 on the top, 2 on the bottom. Right? Is that fine? Because effectively I've added 4 more columns and 4 more rows, and that's exactly the loss which I was making. Is that okay? So now if I have padding of P and a filter of size F, and my original width was W1, can you give me a formula for W2? W2 is equal to W1 minus F plus 1. That we already know, right? Plus, I'll give you the formula and you'll be okay with that. Is that fine? So take the value of F to be 3 cross 3 and the value of P to be 1. What will you get? W2 is equal to W2 is equal to W1, right? If the filter is of size 7 cross 7, what should the padding be? If the filter is of size 7 cross 7, what should the padding be? 3. Is that fine? And you'll get W2 is equal to W1. Everyone okay with that? So now we have a formula for computing the width and height of the output as a function of the input and the filter size and the padding.